Hi, so thanks for joining us. We're just doing experiment 4 now. So let's read this through and then we'll go to the lab and do the experiment and make our observations for ourselves. So we're going to add a little bit of hydrogen peroxide into a test tube and then add a few drops of acidified potassium permanganate. Let's go to the lab and do that, and then we'll take our observations down and do the half and full equations. Okay, so I've got some of these chemicals here. I've got some hydrogen peroxide, clear, colourless liquid, and I have some acidified potassium permanganate. In the bottle, quite often we'll go and change the colour of the bottle or the label. So I've got a sample here, and I have got some white paper. Sometimes it can help just to have a test tube next to you of the solutions before you react them, so that you can compare them. So, sorry about my phone, but this is a beautiful violet colour. Hopefully you can see that in the video. So all we're going to do is add a little bit of hydrogen peroxide in the bottom of a test tube, and then add a couple of drops of this acidified permanganate. Let's have a close look. So I've literally left it and just gone and sorted out some other stuff, and that colour, that light purple colour, has completely disappeared. You can double check that by holding up your test tube behind with a piece of white paper behind. But there's no colour left in that. So we've seen the purple clear potassium permanganate solution decolorize or turn to a colourless solution. And none of my other test tubes have this, but there are some tiny little gas bubbles forming on the inside of the tube. So that's another observation we need to record as well. As a bit of a side note, right? You will see this in the half equation. So let's go back to the drawing board and write up what happens. So we saw that as we added the purple potassium permanganate, that would have instantly decolorized as it hit the hydrogen peroxide. If you add a couple of drops and then you leave your test tube to sit for a while, a bit undisturbed, you will see small bubbles of gas appearing as well in the test tube. So what does that mean? Well, by now I hope you know that potassium permanganate is a really common oxidant. It makes other things get oxidized. So that means it doesn't get oxidized itself. It makes oxidation happen to other species. So the hydrogen peroxide was the thing that got oxidized. So for our half equation, we're going to show hydrogen peroxide. And now hydrogen peroxide could be reduced or it could be oxidized, and this is where it's going to take a bit of experience to know. We also had our observations to help us. We saw bubbles. So we actually saw bubbles of oxygen gas forming. We need to balance this equation, so we're going to need a couple of hydrogen ions, and there's obviously a transfer of electrons here, and we know this is oxidation. We have to write our electrons on the right-hand side. So it's going to be 2 electrons to balance out this 2 plus charge. And reduction, the potassium permanganate was the thing that was itself reduced because it made something else undergo oxidation. So by now you should be familiar with this half equation. I always try to leave some space so I can fit everything in. Remember, we need 4 waters. If we added 4 waters, then we need 8 hydrogens. Then we need to look at where the electrons are. That's 7 plus charge on this side, a 2 plus charge. So we need 5 electrons to balance this out. We've only just left room for it there. There we go. So that's our reduction. So we can see here that for writing the full equation, we've got 2 electrons in one half equation, 5 electrons in the other. There's no common number between, with 2 and 5, except 10. So we're going to have to multiply this by 5, and multiply this by 2. I like to do this so that I don't lose track of what I am doing, and you kind of find your own system. So as we do this, we're going to end up with 10 electrons on each side of the arrow, and they will cancel each other. Okay, but we'll go through and we'll have a look, because some other things may cancel as well. So we're going to write 5 peroxides. That's all that's on the side of the arrow here. So we go down, 2 lots of everything here. 2 16. That's it, because we're not going to write the electrons. We know that they're going to cancel. Back up here, 5 oxygens. 10 hydrogens. Coming down, 2 manganeses. And 8 waters. So I haven't left myself very much room. They can get quite long, so don't stress too much about it. But we can actually cancel more stuff. On both sides of this arrow we do have hydrogen ions. We have 16 here and 10 there. So that can actually cancel and leave us with just 6. So we can simplify this down a little bit more. And that would be our full balanced full equation. Now, to justify how we knew this was happening and why some things have been reduced and some things have been oxidized, there are 2 different ways you can do this. As you know, you could talk about where the electrons are going, or you could use oxidation numbers. So I'm actually going to use oxidation numbers first for this, because it's easier, and this is why I like to teach oxidation numbers. It's just always foolproof. So the thing with peroxide is there is an exception to some rules. The oxygen in peroxide has an oxidation number of -1, and there are 2 oxygens there. So the oxygen atom here is got its own oxidation number of -2. That means that the hydrogens here are going to have each an oxidation number of +1. All right. Here, we don't really have any exceptions. So oxygen here is going to have oxidation number of 0 because it says as an element. And here, the hydrogen is going to have oxidation number of +1. So why I did that is so I can see here that the hydrogen species has not changed oxidation number. So no reduction or oxidation has occurred here for hydrogen. It is the oxygen species that has been reduced. So for my justification, I could say that the oxidation number of oxygen is -1, not -2, that's because there were 2 of them, right? So just one individual oxygen is going to have -1. This changes or increases to an oxidation number of 0 in the product oxygen. And that's how I know an increase in oxidation number indicates reduction has occurred. No, I was right, oxidation has occurred. It's really, really easy to get reduction and oxidation mixed up. Same with reductant and oxidant, and oxidized and reduced. So do just take time to double check yourself, eh? Going to permanganate, so in MnO4-, the manganese species has an oxidation number of, let's have a look. Here the oxygens would be -2, so that would give us actually -8 because there's 4 of them. there's a overall 1 minus charge, and so the manganese species itself, in order to have something positive added to this negative 8 to give us just a negative 1 charge, we have to have an oxidation number of plus 7. As the reaction happens, changes to the manganese ion, so that is just going to have a oxidation number of plus 2. So it's a decrease to an oxidation number of plus 2 in the species Mn2+. A reduction, an oxidation number indicates reduction. Cool. Going with electrons, it's a little bit hard, but you would say here that each hydroxide species is going to lose 2 electrons, and in the process that forms oxygen. Here you would say that each permanganate species is gaining 5 electrons to become Mn2+, and then water as a byproduct. So you can write that as well if you like, but I personally prefer to do oxidation numbers because it just has a bit more of a proof to it. The numbers work out nicely. So thanks for joining us. That was experiment number 4.